Swayam Prabha. Digital India. Educated India.
Okay, good morning. So, in this lecture, I will be continuing the discussion on deriving biopolymers from marine sources. If you recollect, we looked at some of the polysaccharides like agar, agarose, alginate, ulva, and sulfated polysaccharides like carrageenan from seaweeds, red seaweed, brown seaweed, etc. And then we will continue from there, and then in this particular lecture we will talk about various other kinds, for example this chitin and chitosan from crustacean species, and also we will be talking about collagen, glycosaminoglycans such as this chondrite and sulfate, and hyaluronic acid from fish and other marine organisms. Again, we will look at mostly the process of extraction and purification and some of the applications. What turns out is that compared to the polysaccharides which we saw before, we saw several applications related to bioplastics, food packaging, whereas these set of materials that we are going to see today find large applications in biomedical field, as a hydrogel, tissue engineering applications, and so on. Okay, so but I think there is a lot of scope to repurpose these materials for bioplastics as well. Okay, so we will talk about very basic ideas on these topics. The first one I want to talk about is chitin or chitosan. These are kind of very related materials. I will shortly distinguish the two names, chitin and chitosan. So, chitin is one of the most abundantly available natural polymers like cellulose and starch from the plant world. And so, chitin is also a polysaccharide. That means it is going to be a polymer of sugar units. Okay, and you will find the chitin in the organic matrix of exoskeletons of mollusks, arthropods such as crabs and shrimps. Okay, the hard shell that you see on crab or lobster, that is actually primarily made up of chitin. Okay, so that means biopolymer need not be always very soft and flexible. It can be very hard material too. Okay, so we want to understand the chemistry, how to extract it, and how we can use it for various other applications. So not only they are available from this crustacean animals, but also you find them in insects and fungi, cell walls, and algae. But from the commercial production point of view, chitin is predominantly obtained from these lobsters and crabs, even though it is possible to get from insects and algae and fungi, okay, but in a very limited quantities. Okay, so if you look at the chemical details, the chemistry, there is a lot of similarities between cellulose and chitin. Okay, so if you recollect, where do we draw cellulose from? Any examples? Wood, sugarcane bagasse, right? Various other agro waste from which we can get cellulose, mostly from wood and plants, right? And if you remember, the cellulose structure is basically consisting of the repeating units of pyranose, right? So you can see that this is one sugar unit, this is another one that is connected together through this glycosidic bond, right? Now I want you to remember that from glucose you build cellulose by linking via, what is this linkage here? So this is carbon 1, this is 2, this is 3, this is 4, and so this is actually 1. So you have 1, 4 glycosidic bond. Okay, it's a linear polymer, right? Now if you look at this chitin, chitin is made up of another subunit called this glycosamine. And the difference between glucose and glycosamine is that you see there is an extra NH2 group in the place where it's supposed to be an OH group. That's the only difference. Okay, so you take a glucose molecule and you replace that OH group here with an amine group. You have what is called this glucosamine, and then if you polymerize this glucosamine, then you get chitin. So if you look at this structure, the chitin structure and the cellulose structure, you see a very similar picture. The only difference is in this particular subgroup here, right? So here sometimes this amine can be also acetylated. So what you have here is you have CH3CONH, that's called acetylated amine. Okay, so you have two cases. If you have only the amine group, these are all amine groups. So here R is actually H, so it's basically NH2. This is also NH2, NH2, and so on. So okay, so when all these units are amine or glucosamine, we call them as a chitosan. If you have some of the groups acetylated, if the amine groups are acetylated, then we say it is a chitin. Okay, so the chitin that we extract from this crabs and lobster is actually this acetylated aminated groups. Okay, so now if you acetylate this, if you remove the acetic acid from here, then you get this amine group back, and that would be your chitosan. So the chemistry difference between chitin and chitosan is what is there in the functional group here, whether you have amine or you have acetylated amine. If it is acetylated amine, it is a chitin. If it is simply an amine, it is a chitosan. Okay, so I will see later on that typically we first get chitin in this form, acetylated form, and then you do deacetylation, and then you get chitosan. Okay, and the difference between chitin and chitosan is that chitosan is highly soluble in water because of the amine groups, ability to form hydrogen bonds, etc. Whereas chitin on the other hand is very insoluble in water. Okay, and you can see a very small change in the acetylation can induce differences in the solubility in water. Okay, so so that's what I have written here. So chitin is a linear polymer, and it is based on 1,4 linked 2-acetamide 2-deoxy beta D glucopyranose unit. Okay, so this name may look very difficult, but what it means is this 2-acetamide basically refers to this particular group. 2 because it is a second carbon. From the O, there is a second carbon in which you have acetamide, and then you have this the entire unit is called this glucopyranose unit as before. Okay, and in the case of chitin, instead of 2-acetamide, you have basically a glucosamic acid. That's all. Okay, so that's the chemistry of chitin and chitosan. And what happens is, as I said, chitin has a very high degree of acetylation of the amine groups, and then it forms a highly ordered crystal structure, and it has two kinds of forms we call alpha chitin and beta chitin. It's a two polymorphs that is seen. In this, alpha chitin is the most abundantly available, and it is actually characterized by antiparallel arrangement and a strong inter and intramolecular hydrogen bonds. Okay, so hydrogen bonds are very strong in this system, whereas beta chitin is not that common, it's quite rare, and in this case the chains are arranged parallel to each other. So when you're talking about one chain, what I showed here is that one chain. Okay, so now the chain can also pack. Now when it packs, it can pack parallelly or it can pack antiparallelly. Okay, so if it's antiparallel, that's alpha chitin. If it is parallelly arranged, it's beta chitin, and the alpha chitin, which is the antiparallel, is most dominant. Okay, and the reason for this binding is hydrogen bonds. Okay, because of this OAH and acetylated amine and everything. So some of the important aspects of chemistry of chitin and chitosan. So now if you come to chitosan, as I said before, it is basically a derivative of chitin, and what we do is you take chitin and you treat them with alkaline condition so that you can remove the acetic, you can basically do the deacetylation of the groups, and that basically goes from here to here. Okay, so this is chitin. You treat this with alkali, and then this you basically do deacetylation, that becomes a amine group, and this is your chitosan. Okay, so this deacetylation will lead to amine groups, and this can be easily protonated in mild acid solutions, and that makes chitosan very highly soluble in aqueous solutions. Now if you recollect pectin, when we talked about pectin, we distinguish pectin based on high methoxy and low methoxy based on the degree of esterification. Okay, so there in pectin we use methanol to do esterification. Okay, so degree of esterification or degree of methylization is something we define. Similarly, in this case also we call something called degree of deacetylation. The native chitin will have a acetylated amine. To what extent you do deacetylation, that is called the degree of deacetylation, and typically even in chitosan, 100% is not de-acetylated, it's only 70 to 90% de-acetylated. When it is de-acetylated, it is basically called the D-glucosamine. So, this is basically the molecule, and the remaining 10 to 30% will be in the native form. Okay. So, that means when you buy chitosan, you have to look for what is the degree of de-acetylation is in this material. Okay. This ratio seems to be 7 to 90 of the de-acetylated and 10 to 30% in the native form. And so, if you come to the extraction part, basically again we are talking about a very hard shell material, and we can do something called chemical extraction or biological or enzymatic. In the chemical extraction, it follows 3 steps. So, first you do what is called this demineralization, and then deproteinization, and then decolorations. Okay. So, the decoloration is an optional thing because you see that crab shell or lobster shell will have a pigment, reddish or brownish color. So, if you want to have white chitin or chitosan, you may want to do decolorization also using bleaching and other things. So, in the case of biological or enzymatic, what we do is we use bacteria or fungi to do this the first 2 steps, that is demineralization or deproteinization. So, some of the bacteria that are used for this application is Lactobacillus, Pseudomonas or Bacillus and Aspergillus. These are the typical bacteria that are treated to do this extraction. And then for decolorization, like for example, if you remember in the case of cellulose, to do decolorization we do bleaching, and bleaching typically involves sodium hypochlorite or hydrogen peroxide and acetone combinations. Okay. So here is a schematic of the process. So you start with crustacean shells, crabs and lobsters or squid pens, and you remove only the harder part, the shell part, and then you wash them and then cut them into smaller pieces. And typically it involves a grinding process also, so that you make a very powdery material, so that the extraction can be more effective with a small particle size. And so here the first thing is to do what is called this demineralization, which is basically washing with acid, 1 molar HCl added, and then at room temperature it is stirred, and then you centrifuge, separate the precipitate. And then the second process is this deproteinization, for which you use what is called this alkali treatment. So, acid plus alkali treatment, and then again 1 more round of centrifugation, and the remaining precipitate that you get would be your chitin. As you can see, this is the acetylated amine groups here. Okay. So, as you can see, it's a very simple process. It just uses acids and bases to remove the chitin from these crusts. In a way, you can remember that the way that we extracted cellulose also involves this kind of alkali acid treatment, bleaching treatment. The process is very similar. For the chitosan, the process we need is we need to deacetylate that groups. So that is actually done through stirring with again very high concentration, 50% of NaOH, which is very high concentration, to do deacetylation, and then you basically filter, remove, and then freeze dry, and then you get a chitosan powder. So here you can see that the acetylated amine has now become simply an amine. Okay, and this has been achieved simply by treating with very high concentration of NaOH. So that is deacetylation. Now there are other methods, more newer methods that kind of directly take the raw material into chitosan without going through 2 steps. Instead of getting first chitin and then from chitosan, you can also directly get chitosan in a modified extraction process. So again, you start with the powdered or ground raw material. It's directly treated with the 50% NaOH in the first place, so you can do deacetylation in the first place itself. Okay, and then again filtering, washing, and then freeze drying directly give you chitosan. So if you don't need chitin first, if you directly want chitosan, you can follow this process, where this initial process of treating with NaOH is enough to do the deacetylation as well as purification. Okay, so that's all about chitin, and I will leave it to you to find what are the applications of chitin and chitosan. There are a whole lot of applications, as I mentioned already, mostly in biomedical field, but are also edible films and packaging films also you will see. Okay, so I don't want to repeat that over and over. So I think this is something you should look at by yourself. The second important polymer obtained from a marine organism, also from other organism, is collagen. So collagen, I think many of you would have known this. It's an important structural protein. Chitin, chitosan are polysaccharides, but collagen is a protein. That means it's going to be made up of amino acids. Okay, so chemically they are very different in that sense. And the collagen basically it basically offers a structural role in connective tissues, especially in tendons, ligaments, and bones. And and this collagen is supposed to give the enough mechanical property and strength, tensile strength, and flexibility. And collagen is known or purified in very many forms. At least about 28 number of different types of collagens are actually reported. This is because of the differences in the type of crystals they form, the kind of chain arrangement they have, etc., and also from the sources from which it is derived from. So I mentioned collagen is made up of amino acids, and you will find them typically in the form of a triple helix. It contains 3 left-handed alpha chain helices, and they are assembled together through hydrogen bonding to form a right-handed supercoil that we call as a basic collagen unit, and this collagen unit themselves will organize into a collagen fiber. And this triple helix that we are talking about is characterized by amino acid sequence glycine X and Y. So in all the collagen that is reported, all the 28 of them, the sequence will be such that at least one of them will be always a glycine residue, whereas this X and Y can be different. Okay, and this X and Y can be different, but predominantly they are made up of either proline or hydroxyproline. Okay, X and Y can be composed of either proline or hydroxyproline. The third component will be always glycine. It is common. And collagen can also be differentiated into a fibrillar collagen and non-fibrillar collagen. So here you can see that out of this 28 different types, type 1, 2, 3, 5 and 11 are fibrillar and others are non-fibrillar. So whether it forms fibril or non-fibril, it depends on whether we retain the helical structure or not, whether we are breaking the hydrogen bonding that stabilizes the helix or not. Okay, so based on this molecular details, the type of collagen is different, and whether it forms fibril or not fibril is also different. I think I have a cartoon to show this. So you can see that glycine XY, so X can be proline, this can be hydroxyproline, or both can be proline also. Okay, or it can also be other kinds of amino acids. So you see that this kind of a strand, amino acid strand, and then 3 such amino acid strand forms this triple helix structure. Okay, and these triple helix structure, they themselves form, assemble further to form this kind of a fibrous thread. So that's the structure of collagen. Okay, so we also see another term called gelatin. Gelatin is also related to collagen. It's just basically a different form of collagen, especially from a molecular point of view. So what you can do hydrolysis. If you do hydrolysis, you basically break the polymeric chain into smaller units. That means you can reduce the molecular weight. Okay, so typically the undenatured, that is a native collagen, has about roughly 300 kilodaltons, and this is isolated from the specific sources. It could be fish or bovine sources, whereas gelatin is basically a collagen but with a much smaller molecular weight. When the molecular weight is between 20 to 90 kilodalton, it is called gelatin. So it is basically a collagen derivative that has undergone an irreversible chemical and thermal process to break into smaller units. And if you reduce the size even below, then we have something called collagen hydrolysates, which have a molecular weight between 2 to 9. Okay, so collagen, you can find them in 3 different forms depending upon the molecular weight. The native or undenatured collagen, or gelatin or collagen hydrolysates. Okay, and this is a basically a kind of a small oligomer of the collagen unit. So thinking about their properties, they are very biocompatible because it is derived from bio sources, and they are biodegradable because it's a native material, and because of that the collagen and gelatin are highly sought after material for various biomedical application, including pharmaceutical, cosmetics, even food industries also. So now there are recent issues with collagen derived from avian and bovine sources, because there have been reports saying that collagen derived from bovine sources lead to certain diseases like bovine spongiform encephalopathy, PSE, or this TSE, or foot and mouth disease. And also there are other issues like ethical and religious reasons, to derive material from animals. Therefore, the marine sources offer an alternative to bovine based collagen, and fish, jellyfish, squids, mussels, sea urchin, sea cucumber, these are set of marine organisms from which collagen can be derived. However, there are some key issues with collagen derived from marine sources. They are not as strong as, or they are not as cross linkable as the bovine based collagen. Okay, so in terms of property, functional ability, there are some challenges to be solved, okay, from the marine based collagen. So here is a kind of a typical extraction process schematically shown. So what you do is you start with any of this sea animals like fish or shark, jellyfish. You will cut them into small pieces, and then first you will wash and clean everything, and then first thing is to submerge in sodium hydroxide solution, in alkali solution, over a period of day, and then this is lead to decalcification, and then you treat with acetic acid, and then you kind of pelletize with the centrifugation, and then this is basically undergo multiple washing with salt, dialysis, and then freeze drying, and finally you get a collagen. Okay, so again, treatment with acid, base, and salt is very common for any biomaterial synthesis, and that's what we see here also. And the final collagen will be colorless, will have this kind of a very gel-like material. So now the third thing I want to go is this chondroitin sulfate. So chondroitin sulfate is a polysaccharide, it's a linear polysaccharide. So now we are coming back to again polysaccharides, and these are also obtained. The source of this CS is the extracellular matrix of several connective tissues such as skin, bone, cartilage, ligaments, and tendons, but they are not made up of amino acids. Okay, they are not proteins, they are polysaccharides. And then more specifically, if you look at the number of repeating units, typically you do have about 20 to 100 repeating units, and this contains of a dimer, and the dimer is of this N-acetyl galactosamine and then glucuronic acid. You can see that this particular term is this N-acetyl galactosamine, and this is your uronic acid. So you have a dimer made up of this glucuronic acid and then this N-acetyl galactosamine. This forms the repeating units, and you'll have 20 to 100 such repeating units to get this chondroitin sulfate. And sometimes what happens is that in this particular N-acetyl galactosamine, these groups can be sometimes sulfated, especially at position 4 and 6. And so depending upon whether it is sulfated at 4 or 6, you have two types, type A and type C. And then this is can also be obtained from certain bacteria, E. coli or Pasteurella multocida, okay, and also from cartilages of both mammalian and fishery origins like shark cartilage, ray, fin, and zebrafish, dogfish, salmon cartilage. Okay, so these are the raw material from which this can be derived. And again, this also has very good stability, very minimal toxicity, and you can do a lot of chemical modification because of this. You have sulfate, you can do sulfate, you can do sulfate, you can do deacetylization, you can do a lot of functionalization to change the properties, and it also can undergo biodegradation. So because of this, this has been used as an antioxidant, anticoagulator agent, anti-inflammation, as well as anti-apoptotic systems. And predominantly this is not much used compared to collagen, but still there are opportunities to use them as a drug delivery system, scaffold for tissue engineering, etc. And some of the newer application involves that it can be used for regulating cell behavior by binding to growth factors such as cytokines and so on. So, okay, so a lot of applications from a biomedical point of view. So only difference here you see is that it is a dimer containing two different kinds of units, and you can also do sulfate. You can also include sulfate groups in these locations. Okay, so that is the chemical details you want to remember. Again, I don't want to repeat this again. Again, this mostly involves cutting into smaller pieces, treating with enzyme, treating with alkali and bleaching agents to get to this final structures. Okay, so the last one I want to talk about is this hyaluronic acid. So hyaluronic acid, if you have bought recently any of this face masks that you get from this Korean brand, so they use actually hyaluronic acid in their face mask applications. So this is also very highly useful in biomedical applications. So hyaluronic acid or hyaluronan is a high molecular weight, a linear polymer, which does not have this, it's basically based on non-sulfated disaccharide units of D-glucuronic and N-acetyl glucosamine. So basically the same unit as before, like chondroitin sulfate, but here we said it is sulfated. If it is not sulfated, that's basically your hyaluronic acid. So you can see that these are simply OH groups here. Okay, no sulfation here, no sulfate here. So because of this COH group, it is an anionic polymer, and it is also found in connective tissues. And it can be found in both prokaryotic and eukaryotic cells, especially the rooster comb that you see here. That's a very rich source of hyaluronic acid, and also in synovial fluid, umbilical cord, skin, part of the eye is also rich in hyaluronic acid. And it is well known for its lubricity, viscoelasticity, and biocompatibility, as well as immunostimulatory responses. So highly useful in biomedical applications. It's also used for this wound healing, arthritic treatment, tissue scaffolds, drug delivery, and also in implantable diseases. So all these things, whatever I've covered, predominantly are used in biomedical field. Its potential for to be used in packaging or in bioplastic is a field that one should be able to explore. Given that most of them are actually derived from waste of fish and bovine sources, one should be able to get these raw material and then repurpose them for many of the bioplastic applications. Another thing is you also see a lot of combinations, sometimes collagen with the hyaluronic acid, right, and then chitin with collagen. You can also mix match polysaccharides with proteins also. Okay, so a lot of options there to come up with the new formulations to meet a particular performance. Yeah, so any questions or any doubts at this point? Yeah, so that's all I have as of now. I would make one suggestion that we have seen several chemical structure and they all look very similar. It may be a good idea now you take few minutes to go back to your notes. Wherever you discuss these chemical structure, you enumerate on one side. On the other side, you try to write what are the polymer that it corresponds to, and try to see if you can distinguish the chemical nature of each one of them, because it could be very quite confusing to see similar kind of sugar structures, similar kind of things, and a small modification changes everything. Okay, so I think we have few more minutes. You could do that exercise now. And also I have uploaded all the lectures in Moodle. I hope any of you have seen it. Okay, I think except this lecture, I think everything else. Today I will upload this also, and tomorrow is exam. So all the best.